So welcome everyone to my talk. My name is Cyrill Stachniss and I'm from the University of Bonn. It's my great pleasure to be here talking to you about the most recent developments from my group in the context of autonomous vehicles moving in urban environments. And I want to look here specifically through supervised, but also more into unsupervised or semi-supervised approaches that try to interpret laser data and deal with laser range data. So laser range scanner is a scanner which perceives the 3D environment and generates 3D points of the world, and we want to interpret this data. This could be a geometric interpretation that we want to build a geometric model of the environment, but more often it actually is related to semantic information that we want to estimate what we are actually seeing. Object classes, instances, tracked objects over time are quantities that are of interest for us. And I want to, again, introduce you to some of the most recent approaches, some of them just being published, others going to be published in the next 6 months, and telling you what we are up to, what we are doing here in my lab in this context. So the work I'm presenting actually is not just done by myself. Actually, the majority of the work goes to my postdoc Jens Belay and several PhD students. Raini, who was working on the automatic label generation for LiDAR-Based data, Rodrigo Macuzzi working on 4D Panoptic segmentation, Benedict Mersch on point cloud prediction and moving object segmentation, Lucas Nunes on unsupervised approaches, especially for semantic segmentation, Ignacio Vizo on point cloud completion or scan completion, and Luis Wiesmann on compression algorithms. So several of the approaches that I'm going to present here in the next 30 minutes are actually credited to them, so they did the majority of the work. Okay, so let's dive into the details and look into autonomous vehicles and ask us the questions, what question autonomous vehicles have to answer while operating in a real-world environment. So they need to know where they are, they need to know what the world looks like and what happens around them. So that are key perception problems that an autonomous vehicle has to solve. I'm not going to address the where am I problem here, so I'm not looking into localization. I'm also not deeply looking into what does the world look like in terms of SLAM or mapping, something which I've been working in the past a lot, but I won't make it a central part of this talk. We will, however, look into compact representations of the environment that can then be very useful for autonomous vehicles. So it's a little bit related to mapping part, or at least to geometry. But most of the focus of this talk will be on what happens around us. So what are other vehicles around us? How can we do this in a semi-supervised fashion, especially with the goal of reducing the amount of labeled training data that we need. So if we look to the information that a vehicle perceives with this LiDAR scanner, you can see here basically a 3D point cloud being located. One part of the point cloud, there every point is colored, and this is a semantic ID, so a label, for example, for a 3D endpoint belonging to a car or to a vehicle, to a pedestrian, to vegetation or other objects. These are kind of these colored objects over here. And then in the other part of the screen, so over here, we have individual objects being labeled, like vehicles in this example, or pedestrians or cyclists. And here we are looking into instance information. So these are not, this is not the same color for every car, for example, as on the other side. Here we are looking into every individual instance. So every car should have an individual color so that we can distinguish the semantic segmentation from instance segmentation or the instance information. So overall, the information that we're interested in are poses, and which I'm actually going to ignore here, 3D geometry, which plays a role in here, but not looking into SLAM, semantic information, instances, tracking, and then later on also looking to the future, predicting what is going to happen, which is important that an autonomous vehicle can actually make navigation decisions based on the perceptions. So we are basically here in the area of 3D geometry, semantics, instances, and tracking. That's mainly the part that I'm going to cover here in this talk. So let's start with geometry. Let's look into geometry. And again, I'm not looking into SLAM. I want to look here into a slightly different problem, namely on how can we actually store all the information that we are processing. So is there a good way for compactly storing a 3D model or 3D information about the environment so that we can later on retrieve it, maybe even do localization tasks or path planning tasks with it. But the focus here is storing the information on an as compact as possible, in an as compact as possible manner, and trying to be as close as possible to the original data. And this has led us to work on point cloud compression for autonomous driving application. Again, a work done by Louis Wissmann from my group. And here the motivation was that LiDAR scans actually produce a substantial amount, a huge amount of data. So if we have whatever, around 100,000 endpoints per scan, we easily have a large number of scans in the order of 8 to 9 billions per day. These are a large number of points that I may need to store. And the question is, how can I reduce this data with compression techniques? So are there elegant ways how I can take this huge point cloud and compress it into small point clouds? And there's been a work that we have been working on looking into lossy compression. That means not lossless. It means we lose some information, but then get very high compression rates. So this is a small example of a small scene from the Kitty data set. Just a kind of very small patch of whatever, 30 by 30 or 40 by 40 meters of the local environment aggregated into a point cloud. And what we want to do is we want to take those local patches and actually put them into a compression algorithm that compresses this point cloud data into a very compact representation, a very compact code, so that we then later on can actually decode that again, uncompress the map, and come up with the reconstruction of the 3D environment, which may not be exactly the same as the original input data because we're looking to lossy compression, but should be similar. And the key thing to look into is that this data here is fairly large. So in this example, 40 gigabyte of raw data, and want to compress it to a very small code. In this example, 200 megabytes of data. So a pretty large compression that we can achieve here. And the question is, how do we do that? How do we build up this approach over here? And we looked into learning-based approaches, deep learning-based approaches, in order to encode the original point cloud into a very compact representation consisting of a small subset of points and features associated to these points, so that then a decompression part of the network can take those sparse points together with those features and upsample them again towards a dense representation of the environment. So how does this work? So we are having here an encoder and a decoder structure. So we have the input point cloud which is coming here on that side. It's being compressed up to this small code over here, which you can then store on disk or do other tasks with it. And then the decompression part, which then turns this back into a point cloud with an arbitrary density, so an upsampled point cloud again. And so the input part basically stems from a kpconv, a technique for doing convolutions on 3D point cloud data, where you basically select a point and consider the local neighborhood around it and define convolution based on this, which you then, with multiple elements, scale down until you get a compact representation together with a set of features that has been extracted. And from these set of features, we can then upscale this point cloud again with a continuous deconvolution setup where we have our decoder that generates us again a point cloud. The loss function we are trying to minimize here is the symmetric chamfer loss. So we are trying to find for every point in the input point cloud a close point in the output point cloud and the other way around, so that we are not filling the space arbitrarily with data. So we look into the symmetric form over here. And so again, the encoder is mainly using a kpconv, where again we have a point that we are selecting, looking into the local neighborhood and computing a convolutions based on those points in the 3D world. And on the other side, we looked into a decompression layer then for our features. And what we are basically using in those features is a small set of points. So we have a small point cloud, a very sparse point cloud, together where every point has an own feature representation, which allows us to upscale those points and basically generate points in the local neighborhood that represent the original scene. So that we then can generate new points together with the translation vector, which basically tells us how we need to translate those individual points in that space. And if we take that approach, then we are actually able to perform this compression. So we have a raw point cloud where the input data is 3 coordinates, x, y, z coordinate, and the number of points we are putting into, and we're reducing this to a small set of m points, and for every point m, we again have an x, y, z coordinate plus this feature descriptor. And the interesting thing is here that we get a substantial reduction of the memory requirements from 40 gigabytes to something around 200 megabytes in this example. Then you can do comparisons. So in the corresponding paper from ICRA last year, or you can see here the also comparisons with other data sets where you see, yes, there is a loss in the compression, so you can see the point cloud is not perfectly as crisp as the input point cloud, but it's still good enough to localize in this map and do other tasks. And another work that was actually a follow-up work of that, which is currently under evaluation, which is basically an outlook that I'm giving here, is into compact place recognition. So it turns out that those feature representations that we're actually generating allows us also to perform place recognition, similar to a kind of a back-of-words style approach for determining if two places are similar based on this compact code. And this starts to be really interesting now, because that means we can perform localization and place recognition in this low-dimensional representation, in this compact representation. And we don't need to decompress the map until we actually want to show the map, visualize the map. We can actually perform this place recognition in this low-dimensional compact representation, which allows us to do to find places, to close loops, to do global localization just based on this very compact representation, with no need of going back to the original data. Okay, so again, this is something which comes soon, and the next approach I want to talk about, what I've been working on, is an approach called Make It Dense, where Ignacio Vizo was the main person involved in this. And here the question was, once we have that sparse data, can we build more dense maps with this sparse data? So some similarity to the decompression exists, although the approach here is completely different. And the idea was here, what happens if we actually have sparse laser data? And the question is, can we build with a sparse laser scanner a map that looks like a map that built from a laser scanner that has a lot of beams? So for example, we have a 16-beam laser scanner, like a 16-beam Velodyne, for example. And can we build maps with this scanner which look like map built with a scanner which has more beams, like 64 or 128 beams? So what we are actually aiming for is taking a single 16-beam scan, like this one over here. So this is kind of the input data from driving sequence. And can we turn this actually into a map of the environment which looks like this? So which is much denser. That clearly means there are locations where we don't have a measurement, but we want to hallucinate what the world is likely to look like based on this sparse scan. There's a task that we as humans can typically do quite well if you look to the scene and say, okay, that's probably how the world looks like. And we want to enable a computer to do the same thing. And again, here, one of those interesting things is that we can do this basically in a self-supervised manner, which actually the same holds for the compression algorithms before, because there we just need to compare input data with output data. But here what we can do is we can either use multiple scans of those 16-beam scans driving slowly through the environment to get a dense point cloud, or we are actually using a high-resolution scanner and just subsampling the beams and only use 16 of those beams. And this allows us to actually have a more dense points of the world, which I can directly use for an automatic training approach. And the approach here proposed by Ignacio is an approach which basically builds a local TSDF representation from the point cloud and then densifies this TSDF representation. So it doesn't work on the raw point cloud. It actually has a TSDF representation, so kind of a small voxel grid, where in every voxel you don't store occupied or unoccupied values, but the TSDF value, and you're trying to infer how that looks like for the places where you don't have a TSDF value. And then again, the interesting thing is that the scan completion network we are using here can be trained basically in a self-supervised manner if you have a high-resolution scanner or have been driving slowly through the environment, so that you make sure the environment is densely enough covered for the training of this network. Of course, later on you can drive faster through the environment and the network will be able to complete your map. And you can even take the trained network and transfer it to different environments. This works fairly well as long as you kind of stay in a roughly similar area, of course. So you can't, it's unlikely that you will be able to transfer it from an outdoor driving set to an indoor data set, but if you stay within the urban driving domain, that works fairly well. So just a few examples of how this may look like. So this was kind of a local map built from 10 16-beam scans, so 10 VLP 16 scans. And this kind of the raw, if you accumulate those 16 scans and build a TSDF representation out of it, that's what it would look like. And if you take those individual scans, feed them into the Make It Dense network, and then fuse those densified ones, you will actually come up with a model which looks like this. Of course, you can see that some of the structures, like the car, is not perfectly crisp, but the reason is the system has hallucinated how the car looks like, so it's not necessarily a perfectly shaped car, but it's actually pretty close to what you will get before. And you can also see this if you have, for example, faster driving scenes, you're driving through the environment, and even if you aggregate a larger number of scans, like 50 VLP16 scans, driving through the environment with a decent indoor, or not indoor, but inner city driving speed, you will have holes in your data. And by putting this data into the network, you can actually fill the gaps really well and build compact representations, complete representations of the environment with this. You can even feed that back into a SLAM pipeline. We tried that with Zuma, and then actually show that the error that you're doing if you scan match against one of those maps rather than one of those sparse maps is actually better, and you get a substantial increase in performance, especially if you work with sensors which basically have 16 beams or 32 beams, then the gain is really there. And it doesn't only help for building more beautiful maps, it actually also helps the SLAM algorithms in the registration. Okay, now I want to move over and leave the geometric part and look into more into the semantic side. So what are the semantics that we're interested in? And again, looking into approaches where we want to learn semantic information, such as semantic segmentations. So basically a label for every point in the world, saying whatever, it's a car, it's ground plane, it's a sidewalk, it's a building, it's vegetation, or something like that. But other things could also be instance information, saying, okay, that is a car and that's a different car, and that is again a different car. So I want to look into both things. And I want to start with a very brief revisit how we have done that in the past with the RangeNet++ approach developed or proposed by Andres Miliotto 2.5 years ago, something like that, and our current work where we try to circumvent the problem that for these types of segmentations we actually need a substantial amount of training data. So originally we started out saying, okay, we know how to do semantic segmentation in image data, basically using a CNN, taking the 2D image based on labels and turning it into, with a semantic segmentation network, into the output here. And the question is, can we do the same with LiDAR data? The main difference between the LiDAR data is not that it's necessarily a 2D structure. Typically, we have 3D point clouds that we are getting. However, we can basically do the same thing. So in order to turn a raw point cloud into a semantically annotated point cloud, what I can do is I can exploit how the sensor is typically generating its scans. So typically you have a laser with multiple beams which is rotating like this. And so you basically can generate a cylindrical image which you can actually show over here of range data based on a single sweep. And then you have your 2D data structure that you can feed into a semantic segmentation network, label that range image, and then project the range image back into the 3D world so that you're then able to have semantic labels over there. That works fairly well. It has the approach has some problems, especially at boundaries. So some of the work that we have been doing in our 2019 work here by Andres Miliotto was trying to make sure we get the boundaries right and put some extra effort into the upsampling strategies of the network to get a good semantic segmentation. And that works well, but you still need a substantial amount of training data, and this has led to my team, especially under the lead of Jens Belay and other people from Jürgen Gall's group and Sven Behnke's group, work on the semantic Kitty data set and label every single data point in Kitty in order to be able to do that. So it's a little bit frustrating if you want to do that for every type of environment you're operating in. So some of the work we have been looking into is how can we perform semantic analysis with requiring less data. And I want to highlight a few things what we have done. The first questions you may ask yourself is actually full semantic information needed? Do you need the information that something is a vehicle? Do you need the information that something is a building, that something is a tree or vegetation? So is all this information actually needed? And if you want to do full driving, then probably you will need a substantial amount of this semantic information. But for other tasks, it may not be needed in the first place. So especially if you look into a mapping or environment modeling task, then it's often sufficient to say, actually separating moving from non-moving objects, because they are objects which typically disturb your mapping processes. So for some of the problems, clearly not for all, but for some of them, you are probably fine with not taking all semantic classes into account, which makes the amount of labeled data that you need smaller, and also getting that data is much easier. And we have been working then on an approach that was done by Benedict Mersch and Raini Chen to trying to build up a system which allows you to identify what's moving in a scan and what's not moving. And if you kind of accumulate point clouds, for example, of a parked car and a driving cyclist, which is shown over here, so you have scans of a parked car and the different color codes here represent different points in time. You can actually see here that the cyclist is driving. You can basically see here 5 different variants of the cyclist at different positions, partially overlapping and merged, but the parked car, for example, is still the parked car, it's not moving. And so you typically find with, if you want to register scans with a parked vehicle, but you do want to get rid of those driving cyclists or driving vehicles. And so our approach tries to separate this, okay, this is a moving part, so this cyclist is moving, shown in red, but the car is actually standing, it's not moving. We just want to make this binary decision problem, is something moving or is it not moving? And the work proposed by Benedict Mersch recently took sequences of local scans or point clouds generated from sparse scans, stacks them together and basically looks a few scans into the past and takes the current scan and then makes a decision for the current scan what's moving and what's not. And based on this sparse point cloud and the kind of temporal information, the network can make local associations and estimate which part of the scene is actually moving or is not moving. The labels you need to train this approach is just information, is something moving or is it not moving? And so one of the approaches that Benedict was doing here was actually taking these a short sequence of laser range scans. So you basically take the scans from the last half second into account in order to predict what's currently going on, what's currently moving, what's not moving, and network predicting confidence scores about is an object moving or not. And then he was basically taking the prediction that he was actually generating and fusing them in a binary-based filter for every segment, saying, is this actually moving or not, so that you also have a temporal filtering in there, and not a single observation can very easily lead to a wrong classification. So you have here, through the temporal overlap, getting consistent information over time by basically using for those individual objects being potentially identified a base filter or binary-based filter in order to make, in order to provide that track information, what's moving, what's not moving. So even the object stops very briefly, it's still moving, only if it stays for a slightly longer period in time, it would actually be labeled as a non-moving object. And just to give you an idea that this, how well that works, so these are sequences from Kitty. Everything shown in red is basically moving. So all the vehicles, pedestrians, which are moving are shown popping up in red over here, and the rest of the scene basically stays in gray. But for this approach, we still need labels. So it's not that it's a label-free approach. And so we looked into aspects saying, hey, can we actually generate those labels, which are much easier than the full semantic labels, in a more automated fashion? And that was a work which was done by Raini Chen, trying to make an automatic label for this moving object segmentation. And the idea here to do this in automatic fashion is that for the training data, it's fine that we record the training data once, analyze the training data offline, so not doing it online, but doing it offline, and analyzing what is moving, what is not moving based on this data, where we have the full sequential information also into the future on our availability, and can make the decision based on this. So it starts with taking the raw point cloud data, basically running either a SLAM system or an odometry approach. And again, the post information doesn't need to be perfect, we just need to have a good initial guess or a good idea on how that system works. Then you can do some basic removal of moving objects based on the inconsistency that you have found. So you're basically checking which parts of the scene have been seen as free and occupied at different points in time. You can use instance information that you can extract from this, and then separate those instances with a fairly heuristic approach already, and then do a tracking over time and track those objects over time. And the good thing is you can go into the future and back into the past, because this is a completely offline approach. So you can't do this offline on the car, on the vehicle, but you can really well do that in an offline fashion, and through this approach actually generate labels of what's moving in a scene, what's not moving. So you just need to record the data. You don't need to do any manual annotations for this. Just let the computer do its calculations for quite a while, and that will generate you training data for that approach that you then can use to run this on the online moving object segmentation network that I was presenting from Benedict before. So we can turn this the supervised approach basically into an unsupervised approach, and can show that if we do this unsupervised approach in different environments, put all the data together, we're getting much better than using only the initial manually labeled data. You can also do this for map cleaning and generalize this really well to different environments. So moving objects like these spurious objects over here, you can basically automatically remove with this type of data. So this basically turns into a label-free approach. You need a few starting labels, to be honest, but as soon as you have a few starting labels, the approach can run on its own and generate more and more training data that you then can use to retrain your online LiDAR-MOS network, which is really attractive and something that we use, for example, in order to improve our SLAM algorithms by cleaning the data sets with these completely unsupervised approaches beforehand. Okay, can we go even for less supervision? Can we use data in a way also for more complex tasks, let's say again for the full semantic segmentation or even panoptic segmentation tasks with using a smaller amount of labeled data or even no labeled data? So we will start here, we'll look into a contrastive learning scheme that we have been using in two different approaches, where the idea in contrastive learning is that you actually generate pairs in an unsupervised manner, saying two things are similar or two things are dissimilar. And you're basically learning a feature representation or representation with a neural network that where you can say, okay, two things which are similar should be closer in feature space, and two things which are dissimilar should be further away in feature space. And typically, you have quite good heuristics to actually generate those positives and negatives examples. They don't necessarily need to be absolutely perfect. But this allows you to come up with an internal representation which is learned in an unsupervised manner as a starting point for your networks later on for further downstream tasks, and then train it with the label training data that you have and just kind of do a fine-tuning of that network if you start with a representation which allows you already to separate instances, for example, really well. So just as an illustration, maybe you have image data, just as a matter of illustration, taken from the same place, like here the Altstadt in Bonn, and you have different images that you have been taken which look very, very different, but you know they have been recorded at the same point in time and maybe have a rough prior where they have been recorded, and other data which has been recorded either at a different point in time or a different place, depending on what you want to model. And then you can say, okay, given that I know that I recorded it nearby in time, those places should look similar, or my feature representation that I want to generate should make them similar, but the others should be made dissimilar. If you look into video segmentation, you can just take consecutive frames should be similar, frames which are further away in time could be dissimilar. So they're fairly easy ways on how you can actually exploit that. And this was work done by Lucas Nunes, working on contrastive learning for point cloud segmentation, basically segmenting, trying to identify different relevant segments, instances, and doing this in an unsupervised manner. And he started, especially that works for outdoor driving scene, will not work for indoors, or most likely not work that well for indoors. We extract the ground plane, make a ground plane removal, some clustering, a little bit of heuristics. You will get a rough instance or segments information out of your 3D scan. And now we can actually use this segment information in order to generate good samples. So we have a point cloud and we have some segments extracted with this fully heuristic technique out of our data. Then we can do some data augmentation, so take out parts of the scan, for example, removing some elements in order to get robustness in here. Then we have our neural network, which tries to build up a feature representation that encodes the local surroundings, so it extracts points together with feature information, and we want to have this feature information should have certain properties so that it allows us to move in the end two segments, two points which are sampled from the same segment in the scan being actually close together and others being further apart. So we have the segment pooling layer where we have the segment information and then a projection, basically taking just the max pooling so that we make sure every segment will generate, or is most likely to generate, the same features by always going for the maximum. And then we get, based on the representation that we're actually getting, we are computing our contrastive loss. Saying, for example, that those two segments should be similar, but those segments should be dissimilar from each other. And just by providing this as a pre-training of the network, running our system, and then later on adding label training data, doing a supervised fine-tuning on the networks, we actually obtain really good semantic segmentation results. So what you see here is ground truth on top and the results of our approach just using thousands of the labeled data. So this is the data from Semantic Kitty, and here we just used 0.1% of the training data, and this allows us to still provide a quite decent semantic segmentation and instance information as well for this network, for this environment, by using this pre-training where we are generating an underlying feature representation from which we start our supervised learning that was generated in this unsupervised manner. What Lukas is currently working on is class-agnostic instance segmentation, where we go a step further and analyze the segments more carefully. So there's basically a region of interest which makes proposals, and then we see if we, for some of those proposals, we know can estimate what's foreground and background, basically build a graph of those points, then run a graph cut to get a better separation of what's potentially foreground and background, that we then can actually go to a class-agnostic instance segmentation and segment those scans in an unsupervised manner into those objects and then get better and better results. This, having semantic information and instance information, can lead us then to panoptic segmentation, and I want to look very briefly into 4D panoptic segmentation. What means 4D panoptic segmentation? It means we have our the information about our semantic labels, we have our instance labels, and we have tracks over time. So we can associate objects over time and have consistent labels over time. And we built here based on existing 3D panoptic segmentation systems. Also, Abhinav, one of the organizers here, has built a great panoptic segmentation systems in the past. So we are using an own system, but it basically doesn't really matter what you're using here. So you have your 3D panoptic segmentation network, and which gives you information about the semantic classes and the instance information. And what Rodrigo Marcuzzi, who was doing this work as the main author, has done, built a contrastive association network and then a data association module, which again uses contrastive learning in order to build up data associations between objects and then performing a data association so that he's then able to actually track those objects over time so that we have a fully labeled output scene with track information, obtaining a full 4D panoptic segmentation network. And the key contribution that he has been doing here is basically this contrastive association network and the data association module that was in there. And I just will go very briefly over it. So we basically have point features with our input, so our points together with feature information. Then we have this contrastive aggregation network where we reduce this to a single instance feature. So every instance has its own feature, and then we look into points coming from the same instance. They should have similar features. Those coming from other instances should have separated features. And again, similar as before, we can do this by taking the current scan and scans from the past, but also from the future. So something which runs offline, this training step clearly, where we say if we know, at least for those objects, we can separate really well. We know kind of the green ones are positive examples, so positive samples, and we can then take the green one and associate with one of the other ones, the red one, get our negative examples, and we can use this as contrastive pairs for our training. And so what we are later on doing then, once we have the trained network, given that we have two segments that we abstracted, we take our contrastive association network. This provides us with basically a similarity, so it's a cosine similarity computed on this single feature representation for every instance, and this basically encodes the appearance. And then we combine it also with the center of those, the distance between the centers of those objects, feed them, join them, and then basically get an association cost, and then can run an association algorithm such as the Hungarian method to get our data association. And this leads to the fact that we can actually perform semantic segmentation or 4D panoptic segmentation. So we have the semantic segmentation of the scene, which is not depicted here. Here only the instance is shown, where you see that the tracks have consistent color over time because the vehicle is able to make the correct data associations based on this 4D approach. And with this, I'm coming to the end of my presentation, and I hope I've given you a nice overview on what we have been doing in the lab in the last, let's say, 1.5 years, what are techniques that have been working on in order to interpret LiDAR data which comes from a vehicle driving in urban environments, looking into compression algorithms, scan completions, and working on semantics, where a focus in my group was kind of how can we reduce training data or need less data, either through pre-training or simplifying the labeling problem so that we can actually train our networks in a more effective manner. And again, this was not just my own work. This was work done by Jens, Reini, Rodrigo, Benedict, Lucas, Nacho, as well as Luis. And with this, thank you again for inviting me, for having me here, and I wish you a nice and great remaining workshop day. Thank you very much for your attention.